Thank you, Vlad. So, because some of the people have changed, I want to recap very shortly just the essential properties that we need to know about time crystals. So imagine that you have a material that is homogeneous in space and epsilon changes in time. What I've showed you is that what happens is that this material will have bands, and the dispersion in this material can be described as band and band gaps, and it is rotated by 90 degrees with respect to what we know from 1D photonic crystals. So the band gaps are in momentum. The implication is that there are values of momentum right here in the gap where the modes, the Fouquet modes, are exponentially amplified and exponentially attenuated. The exponentially attenuated are not interesting. The exponentially amplified are the interesting ones. Keep in mind that this system, because of this modulation of epsilon in time, the system does not conserve energy. But because the medium is homogeneous, the system conserves momentum. So as a result of that, what will happen is that the modes that are sitting right here with the k vector in the gap can be amplified exponentially at the expense of the modulation. So in other words, it sucks energy from the modulation. Okay? In order for that to happen, to have a band gap, then you need to have a significant change in the refractive index, or in epsilon, and it needs to occur on a scale that is comparable to the optical cycle or shorter. Otherwise, you don't have a band gap. And I'll talk about it now with respect to experiments. That's really the essential ideas. Now, since it has been asked and so forth about optical parametric amplifiers, in optical parametric amplifiers, there's no band gap. The conservation laws shrink the band gap to a point, to zero. There's no band gap. There's only one point, which is resonant, which means that you need to obey energy, conservation of energy, and momentum. Whereas when you have a band gap, you do not conserve energy at all, which means now that you can be in any direction within the band gap, any direction. So let's say even 90 degrees, let's say that your material is modulated like this, is homogeneous, and is modulated by something. Let's say by some capacitor or something, and the probe propagates here. No way you can do any phase matching here, okay? And it will be still amplified, provided it's in the band gap. That's the story about this. I want to recap a few more. Let me see, maybe now it will start. So we looked at temporal boundaries and so forth. I want to recap quickly what will happen. So spatial interface, we know we have Fresnel reflection. In a temporal interface, just in time, what will happen, you have time refraction and time reflection. Both of these will have a different frequency. Why is that? K is conserved. So K is equal to omega divided by the speed of light in the medium, which is omega, the frequency, times the refractive index, divided by the speed of light in vacuum. So therefore, if you change the refractive index, you need to change in K is conserved, okay? The value of K is conserved. Now you will have that if you have, let's say at the beginning here, you have omega, let's say omega 1 times n1 divided by the speed of light in vacuum, and here you'll have omega 2 times n2 divided by speed of light in vacuum, okay? So the ratio between the two frequencies is exactly the ratio between the two refractive indices, okay? So both of the time reflection and the time refraction will move to a new frequency. It is okay to think about it as Doppler effect if you're just interested in the frequency. But what will happen next, at the time reflection, the fact that you have a time reflection, it's not a Doppler effect. And I told you about it, that the time reflection of light has never been observed. This is an experiment with water waves. With those of you who don't remember, this Matthias Fink did it, not with electromagnetic waves, but with water waves. And what he did, he had a chamber with water, and he put in the Eiffel Tower, just on the surface. And then it created waves that go away, disperse, and the Eiffel Tower disappears. And then he drops the chamber abruptly. The waves on the surface are driven by gravity. So therefore now, if you change gravity, then you've changed now the wave, the nature of the wave. You're like modulated epsilon in the medium. As a result of that, you get time refraction, which continues to go away, to run away from the center of the chamber. But part of that is also coming back, time reflection. And the waves that come back have conjugate phase. So they reconstruct the Eiffel Tower. So here he dips it in the water. You see the waves going out. Okay, he removes the statue. And now he drops the chamber. And you see that, okay, let me do it again. Okay, it goes out. Now he removes this and drops the chamber. He drops it, and now he drops the chamber. Oops, the time reflection wave will create the Eiffel Tower. So the phase is conjugate. Okay? Again, the difference is right here. This is photonic crystals, this is time crystals. So the mathematics is similar, but there are some issues. And here I talked about put a point source. If you take a photonic crystal and you put a point source with the point source that is frequency is in the gap, the solutions are two frequencies. Okay, the solutions are k vectors that explode in time. Okay, so the solutions like that. So as a result of that, but the system in a photonic crystal conserves energy. So as a result of this, that you will have only the part, this part and this part are not physical. So the point source was here, and it can emit only into evanescent waves. Photon flux is 0. Here, if you look at time crystal and the time equals to T0, you create a flash of light. You have now two exponents. One goes up with time, the other one goes back in time. You see, this is Z, this is T. But now here we are restricted not by energy conservation, but by causality. So this is dead, and what you get is the two solutions, the two Fouquet modes that grow up and decay. The one that decays is not interesting because it's immediately overtaken by the one that grows up. Which means that any light source that emits in the momentum gap can be amplified by the modulation. Okay, and here I showed you this, and then I'll go to the emission part. So this is what happens when you have a pulse that propagates, that is propagating, is associated with the band. So we created a wave packet of k vectors here, k vectors frequencies right here, and we launch it, and you can see that it enters the crystal, so it creates time reflection, time refraction, and right here, the pulse undergoes some dispersion according to the slope here. Okay? What happens in the gap? If you create a wave packet here in the gap, now the pulse comes, it splits in two right here, time reflection and refraction, then it stops and grows in amplitude because it couples to the Fouquet mode growing exponent, and here it splits again. So this is how it looks. So now let me jump down.
Have you modeled this question? The material model, or it's just...
No, here we just took refractive index.
I need to speak with my doctor's nurse.
I'm getting your live. Professor Nermanov, you're live.
Yevgeny, put yourself on mute.
You're live.
Yes.
Okay. So this is what I told you. So what we did here when we talk about emission is the following. First of all, we looked at classical. I'm just recapping what I said, because sometimes, trust me, it takes several years to get the intuition. You can do a lot of nonsense at the beginning, which everybody falls into this because a lot of things here are counterintuitive. Okay, the comparison is helpful, but it's not, the similarity is not exactly that. Okay, so what we did here is the following. We wanted to know, in order to solve for what happens for a classical antenna or classical dipole that emits in the band gap, to know what happens to it. So what we did, you need to solve, this is all classical Maxwell equations that I wrote about, that I showed you, the response to an impulse. In other words, you need to create a source that emits at a given time. Let's say time equals 0, okay? So for that, we needed to find the green function. What is the green function? In electrical engineering, we call it the impulse response because the system is linear. Physicists like to call it green function because they did not know that it is a general feature of all linear systems in the world. All of them have impulse response, and you can work with superposition. That's how it is. Anyway, so the green function or the impulse response to a flash of light, of electric field, looks like this, and it is restricted by causality. It looks like this, which is kind of simple, yes? And so now, the next thing is, let us construct some kind of a current source by looking at a general, completely general current source, by looking at this, at the response of the time crystal to the impulse response. So you can construct any J of t, any current source like this with any function, using the impulse response or the green function. So that's what we did. So what we were interested in order, first of all, to gain some intuition. So we looked at something that emits only in one direction. So you can think about it as an emitter, the directional emitter, that emits only to k minus k, whatever, at a given frequency. And we calculated just by like this through the impulse response, we constructed that. And we wanted to see what happens when you look at the emission. So the first thing that we looked is what happens when your classical dipole emits in the band. So it's when it sits on the band exactly, it means now that the relation between omega and k are exactly this point, like here. What we saw is that you get amplification by the modulation that is more or less linear in time. What happens if you get off the band into point B? Then the amount of, so it can amplify a little, back and forth, they oscillate. This is not surprising because you need, right here, what you need is phase matching. But what happens if you are in the gap? In the gap means now that the direction of your emitter corresponds to the momentum gap. So let's start first of all when the modulation is exactly sits right here. This is half the modulation frequency. Okay? When the frequency of the radiator of the dipole sits right here. Then what you find is that the amplification is exponential, so this is a logarithmic scale. Okay, let's go off the dispersion curve, right here. And you ask yourself what will happen. You will see that amplification at the beginning is a bit slow, but then goes up exponentially also, which means that it is in the band gap, phase matching is unimportant, not even for the real part. Okay? In the red, you see here now the imaginary parts of the frequency. So you can see that right here in the middle of the band gap is the strongest frequency that can be amplified. So what we did next, here this is exactly the same. Now let's take a point source. How do you construct a point source like a classical atom? You construct a point source by looking at a point source by superposition of directional emitters to all directions. So when you have a point source like this, it will emit at a given frequency, omega 0, to all directions in 1D. You can do this similar, okay? So this is this. It emits at some frequency, whatever it is. Now, if it emits to all directions, because it's a point source, there will necessarily be a region right here that will fall onto the band gap, and this will undergo amplification. It doesn't matter that it doesn't sit here, which means that it's not synchronous. It's not synchronous, Evgeny. Huh? Parametric amplifier needs to be synchronous. It's not synchronous at all. So it's somewhere here. But the directions correspond to all directions and it's some frequency. Not synchronous with the modulation at all, because energy is not conserved. So what will happen to it is that at the beginning, at time equals 0, you have a little bit, and then this becomes exponentially amplified. And it becomes narrower and narrower because the strongest amplification is right in the center. So that's what happens to it. You see at the beginning, you have all of them start like this, and then this shows you what happens at the beginning, and then it becomes narrower and narrower and narrower. As time goes by, it becomes more and more monochromatic. And strangely enough, if you think about this, is you see, okay, here we are in the band momentum gap, here we are in the momentum band. So the transition from here to here, it should be maybe something will happen as you get closer. Maybe at some point you'll get, as you get closer, maybe you'll get more and more emission. It turns out this is wrong. Actually, what matters is the density of states, which is of momentum states, not energy states, which is defined opposite of photonic crystals because it's momentum states. And actually right here, if you sit at this point on the band edge, slightly to the left, into the band a little bit, then the emission rate is 0. But if you flip to the other side, emission rate now goes exponential. Extremely interesting. And yes, some of you actually notice that this has to be an exceptional point. It is true. You can get exceptional points also without any gain and without any loss. It's in our paper from 2011. When you looked at a periodic system in space, and we showed that the transition from propagating waves of Maxwell equations, classical, to evanescent waves, there's always an exceptional point right there. Anyway, so this is this. Second thing after that is that, okay, now we need to quantize the system. And there are several deep reasons why we wanted to quantize the system. Part of that has to do with spontaneous emission. Part of that is to generate questions that we do not know how to answer. And you will see quite a few, okay? So the equation that we have, the classical, looks like this. Okay? Now, the first part of that, you can say, okay, let us first of all try to do something that we know. In other words, to quantize the field in some material. And the fact that epsilon changes in time will come. Usually what we do, forget all this part, what we do when that we look at annihilation and creation operators, okay? And usually what we have here is a constant, just epsilon. So now epsilon changes in time, you can guess, and it will be an intelligent guess, but not very hard, 1 over epsilon. But it turns out that there is a new term, which took my guys quite some time to find the correct one. And what this means is that the modulation in the medium creates pair of photons, vacuum fluctuations, and because momentum must be conserved, not only classically, but also quantum, then what will happen now, you are creating pairs of photons in k and minus k, or annihilating pairs of photons. Why is that? Because momentum must be conserved. So if you think about this, let's say that I have, like one of the good questions that I was asked in the break, let's say that you have a quantum dot that is a single photon emitter. So what will happen is that quantum dot, okay, so it's a single photon emitter, it emits 1 photon. That photon induces emission of pairs, of a pair, okay, in counter-propagation direction. So the total momentum is the same, but the energy of the photon now is 3 times, because you have started with photon at omega, now we have 2 photons, k minus k, of the same frequency. Keep in mind, there's no need for coherence in this business. In other words, the modulation is classical, not quantum at all. You can do modulation as you wish. And you are generating now, and you don't have atomic resonance, yet the photon that you have, of the single photon, induces emission in a non-resonant way, okay, of pairs of photons, always pairs, okay? The next thing is now, okay, now let's say what happens to these 2. So each one of them will create another pair, each one of the such that the total momentum is conserved, but the number of photons goes up exponentially, and the energy, of course, that in the electromagnetic field goes exponentially. Yes, you want to ask?
The first thing is, what happens if you are near epsilon 0?
I will get to it. I will get to it. I'll get to it. And this is, of course, a very good question that part of it we don't know how to answer. We know only part. And it's actually, there's a lot of deep issues here. Another thing is that we can calculate, given this, we can actually calculate the Fermi golden rule. Which means that it will tell us that given that you have an atom in excited state, okay, what is the rate of radiation? What is the rate of decay of that atom? So I will tell you parts of that. Okay, so this is, first of all, let's talk about photon generation in a PTC like this. So the first thing is, let's look at what happens in the band. So in the band, let's say 0, whatever, okay? Number of the photons in the band oscillates with time, which means that it cannot accumulate. But the number of photons in the gap blows out exponentially. So formally, if you think about the mathematics of this, you can think about it as, okay, so what does it mean to do second quantization? We just look and count the population of the modes in the system. And if the mode in the system is a Fluke mode, that means that we just count how many are there. So it's simply said, but not exactly correct. Okay? So, yes?
So it looks like the fluctuations are somehow periodic. Is it? Or it's
not really. It's an artifact or not long enough. Okay. So the quantum model in homogeneous medium yields amplification of amplified photon generation in a band gap. The density of the photons goes exponentially. Energy is drawn from the modulation. Next thing is a big question that we don't know how to answer. We know to calculate the beginning of the process, but not more. And I will tell you a little bit of what more we know. So let's say that somehow you have an atom that is in excited state, right here. Okay? And you put a photon in the, and that it sits here, okay? In the PTC. So one avenue that it can do, it can emit one photon in an ordinary emission, nothing to do with the PTC, just emit one photon right here, okay? And relax to the ground state. This is this. Or it can go up and down, which is what we call Rabi oscillations. But now, let's suppose that this photon, that the atom remains in excited state, and somehow a pair of photons is added to it. How a pair of photons is added to it? Let's say by vacuum fluctuations that are exactly at the K that corresponds to this. Okay? So now we have the atom in the excited state with another pair of photons, one in K, one in minus K. So now the atom now can go down here by adding one more photon. And then it can go down here, okay? And going back here because it can also annihilate a pair of photons and go up. So it can close a circle like this. But it's not only that. It can actually go to the next time and to have another to stay in the excited state and have now two, which can go down. So actually to go and calculate this, it diverges. It diverges. This system, it's easy for me to say it's chaotic, but my good friend Nimrod says it's not quantum chaos, but the system is highly unstable. So what is the kind of questions that one would ask, for example? Okay, so we can't tell what will happen because it diverges. You don't know, we can't calculate numerically, and we tried with asymptotic. So far we're not able to calculate, but maybe there is hope. But there's another thing that we can do. We can actually calculate the lifetime of the atom and at least answer that. So lifetime of the atom is what I told you before. So when it turns out that when you take the atom, the excited state from being here to here, closer and closer to the band edge, it turns out that what really matters in the emission rate, is the density of momentum states. And if you are on the band edge, slightly into the band, the atom will live forever in excited state.
And energy is taken from modulation of epsilon, right?
All the time. And you create coherent, that's the point, you create coherent photons in this business. This is what the amazing part. It's not antenna. Think about the atoms, everything is in thermal, the atoms are in thermal states. So let us know, go a bit, so this summarizes it. I have a long presentation on this.
Some imaginary path in epsilon, would it resolve all the singularities you have to deal with?
We tried. We didn't find this. It helps us in another place. We looked at what happens in a spatial interface, okay? Imagine that this is, you come from air, okay, or not from, yeah, we come from air, this is air, and this is ENZ, okay? From air to ENZ, you will have a total internal reflection, because air index 1, ENZ, epsilon is smaller than 1, okay? So, you have total internal reflection. And now let us modulate just this part, not air. Air, we give it 1, modulate this. I have some very nice results on that, some analytic, some numeric. It is extremely interesting because what will happen now is the following. The system is, the system now is passive, and you ask yourself, okay, what will happen to it? So before going to time crystals, let's just give it one kick up, okay? But still remain, so you are still remaining under total internal reflection. You change epsilon, let's say from refractive index 0.4 to 0.6, okay? What happened is that because it's total internal reflection in space, the photon flux comes here. What you have inside is photon flux 0, it goes down, and the electric field, magnetic field goes down exponentially. The very fact that you gave it a kick, creates a propagating wave in the medium.
Handling.
Okay? And also creates a phase conjugate reflection. So if you come at an angle, it creates a phase conjugate reflection. Okay, so Maxwell equations, I can accept that. But now let's think about this in terms of amplification. What does it mean now to generate something? We are used to the fact that any optical amplification is driven, you need to have photon flux, real photon flux. But if the photon flux is zero, then how come you have induced emission inside? You created a propagating wave. So it turns out that if you put a little bit of imaginary part to the epsilon here, this explains it, supposedly. I don't know if the rates are really corresponding to that, because what will happen now is the total internal reflection is not really total anymore. And the modes that go in now have a real flux, and this maybe a real flux can induce emission. It's a tricky business, so this one is resolved, but not in a passive medium, and what I told you now is passive. No amplification, index is just real, so we don't have the full picture of that yet.
In that regard, going through zero, when the pulsar goes to zero, is particularly interesting.
Of course.
When you go to static form,
Of course.
Wavelengths, phase velocity, so that's a zoo.
So they are absolutely right, and the immediate question is what will happen to the band gap if you play around zero, maybe even negative. But let's say it's real. I don't want to go to imaginary because it adds other complications. Real. So you play around zero. We don't know yet. There are some questions that we tackled, some questions that lead to contradiction. I'm telling you, this is a tricky business. So, yeah, yes?
So can you go to the previous slide? So here, my understanding is that you are saying that your atom is excited, and your atom can be coupled to this plus minus k.
Yeah, so vacuum fluctuations generate a pair of photons with the same k minus k.
Right, but I think for this for you to make this assumption, you need to assume that there's a strong coupling between those photons and the atom, correct? Are you
Not necessarily strong coupling.
In phase scattering?
Yeah, so I did not want to put it in a cavity. I can put it in a cavity and force it. Yeah, I did not want to. I left it. It's 1D. We don't know how to solve it anyway, but so that's why. Okay.
My question is.
So yes, you can put it in a cavity. If a cavity is bigger, much bigger than the wavelength, then it is the standing waves are dense enough, so it's not a problem. You're looking at this frequency region, so you can play this trick, and then you ask yourself, okay, so I have vacuum fluctuations that generate a pair of photons there, and the photon. What is interesting is that if you are on the band but close to the edge, then you can go as high as you wish. Why? Because the rate of decay is suppressed because of the density of the states in the photonic gap. So what?
Saturation regime here?
No, I didn't want to. I did not introduce it. So of course you can all add some additional effects. But what I did is the simplest. Atom, vacuum fluctuations in the proper K, and let's see what happens. So you would think that if you have more and more photons that are at the proper K as the one that can be emitted by the atom, they will induce stronger and stronger emission. Yes, because of induced emission. That's the whole idea. Induced emission is proportional to the photon flux. The emission rate is proportional to the photon flux. Now this is correct as long as you are not near the band edge. Because if you are near the band edge, the density of momentum states is zero, and then the atom, no matter how much you add to it, will tend to stay. Okay, so based on this kind of diagram, we were able to calculate actually what happens to this state as a function of number of photons and so forth. But the whole process we can't calculate.
But your vacuum is not really the vacuum, right? Because you still have the drive from the PTC. So.
No, the PTC creates two pairs of photons. So that's the kind of vacuum that we are interested. Yeah, but they can be created at any momentum in the gap. So this is more or less some of the ideas that we looked at. Some of that we solved, some of them we didn't. So there are three basic cases of emission by a two-level atom in a photonic time crystal: oscillating, linear, and exponentially growing. The difference between emission in a photonic crystal and a photonic time crystal is that energy conservation here is a photonic crystal is restricted by energy conservation, and photonic time crystal is restricted by causality. The very fact that energy conservation does not restrict us allows for exponential amplification. Dipole emission always exponentially explodes regardless of frequency in all the directions of the band gap. No phase matching, and you don't need to be on the dispersion curve. Spontaneous emission in a photonic time crystal tends to be 0 on the band edge and infinite in the gap. So that immediately says, okay, so there must be an exceptional point. You are right, there is an exceptional point. The band edge is an exceptional point. Emission in the gap becomes narrower with time, monochromatic when time goes to infinity. And the final one is, let's construct a proper resonator and select a preferential mode and have a laser that has no atomic resonance whatsoever, started by quantum fluctuations. The next part is like Cherenkov, that's relativistic radiation in a time crystal. Okay, so what you see here is, practically speaking, is Cherenkov radiation. Maybe I have better slides on that. Maybe let me show you slightly different slides on that.
May I comment? I think in Russian literature, if you
I give reference to Ginsburg. I am familiar. I knew him personally because his grandson did his PhD at Princeton. So he used to come every year, give a colloquium. So I met with him every year.
But the Cherenkov is discussed, right?
Yeah.
The transition radiation.
Transition radiation, that's correct. So there's issues there. So what he did is correct. But how do I want to get rid of this presentation and put another one. I have one that is better than that because it belongs to a student of mine. Let me see how.
Just in case.
Yeah, this is the one. And now I go to, when do I, maybe it's better to change the display now, no? No, it doesn't matter.
Let's see.
It's okay in terms of display?
Yeah.
Except that I need to get rid of this, huh? Hide. Okay, so that's the story. So let's look at Cherenkov radiation. We have some fast electron going into, so maybe I will start one earlier. So what we want to know is what happens to Cherenkov radiation. Go. I want to start one. Okay, so Cherenkov radiation, as you all know, it's a shock wave, okay? Discovered by Cherenkov and Vavilov. And what we want to know is what happens to Cherenkov radiation near a photonic crystal, something that is periodic in space, and near a photonic time crystal. So in a photonic crystal, Cherenkov radiation, actually this was solved by Smith-Purcell. It's called the Smith-Purcell effect. You can get phase matching, you can add a quanta of momentum by the periodicity in space. And in a time crystal, that's what we are interested to know. Okay, so again, if the medium is uniform and stationary in time, what you get is Cherenkov radiation discovered by Vavilov and Cherenkov. And the cause of that is the shock wave of the electromagnetic wave, which means that there is a threshold, it's called the Cherenkov threshold, where the electron needs to propagate faster than the speed of light in the medium and create a shock wave. You will see a simulation in a moment. Now, if your medium is not homogeneous but modulated in space, what you get is that the medium can give or take a quanta of momentum, lattice momentum, and create phase matching. And the question is what will happen to a time modulated medium. Okay? So that's the story. So if you think about a relation between omega and k, what you need here is this. You need to have a threshold of beta is the relation between the speed of the electron and the speed of light, times the refractive index needs to be larger than 1. Smith-Purcell have shown that if you are below the Cherenkov threshold, so there are beta times n smaller than 1, then the lattice can give you momentum, and you can still get Cherenkov radiation below the Cherenkov threshold, the Smith-Purcell effect. And what you will see here is that the temporal modulation can give you a kick, a boost, okay? And you can get now a boost of energy from the modulation. So first of all, free electron radiation in time-modulated medium. So the story is like this, very similar. And changing in time is not analogous to changing epsilon in space. Why is that? Because if you have epsilon. Okay? So this is the wave equation in homogeneous space. And notice that you have two terms now. And we again find the Fluke modes and so on and so forth. And the green function that I told you before. This is like the flash of light. Yeah. So if you are above the, what will happen now if you are above the Cherenkov threshold, the modulation of the medium can give you harmonics of the modulation field. And from that you can find the dispersion relation. And if you are below the Cherenkov threshold, you'll see just the modulation. So let's see how it looks. Okay. So first of all, free electron. I want to skip these. We can discuss them later. So we start with the electromagnetic, the dispersion modes right here, and this is the band gap. And actually, what will happen now, if you are above the Cherenkov threshold, you'll get all the harmonics that are given by the modulation. This is what happens when you have a, okay, let me show you this again. This is just a simulation of Cherenkov radiation. So you have a homogeneous medium, stationary in time, comes an electron. You are below the Cherenkov threshold. So when you enter the medium, because of causality, you create an information circle, and then after that, the electron does not radiate at all. Why? Because it's at constant velocity. Okay, so here, beta is equal to half, and it just shows arbitrarily this. Now let's see what happens when you are above the threshold. When you are above Cherenkov threshold, you get a familiar plot of Cherenkov radiation. It looks like an arrow, like birds swimming in a pond. Okay, there is, you have shock waves because of surface waves, not gravity waves. Okay, and you can actually here do the Fourier transform of this, and you find the dispersion relation between kx and kx and ky and so forth, all the directions. You can actually determine the directions. Now let's look at the PTC. This is below Cherenkov threshold. The medium has no periodicity in space at all, but it radiates. Let me show it again. Okay, so it's a photonic time crystal below Cherenkov threshold. If you look at a single modulation, then already in a single modulation, Ginzburg was able to show it, and he showed it, called it transition radiation. He actually looked also what happens when you modulate it periodically or as a general function. There's one important thing that he quite missed here, actually several. He could have done it 40, 50 years ago. And some of them is the quantum aspect. So again, this is what happens, the dispersion relation. So this is your electron right here. And it emits forward and also backwards. The way that we usually think about Cherenkov radiation is that the electron creates like a spearhead. But here it creates something different. You see that there is radiation. The only place where there's no radiation is on the axis, forward on the axis. Okay? And this again, it shows now this is above the Cherenkov threshold, and what you get above the Cherenkov threshold, you will see there are several periodicities here. There's this one, and there's the shock front. So there are effects also below threshold where there's no normal Cherenkov radiation, and also above threshold. And it is related to superlight Doppler effect. You can find in the books, as you can see. Okay, there are quite a few of them. And here we are looking at, so I couldn't find this morning the simulation. We have also the simulation. This is the result of it. But the movie I didn't find. So obviously the question is what will happen. Okay, so far everything is semi-classical. You don't need quantum for this. But what will happen when you do what I did before and quantize the system? Let me skip all of that. Okay? Never mind all that. Okay, so now let's quantize the system. So I want to quantize the system and to look at what happens in the same time crystal, where now I will have the electron. So the Hamiltonian for the electromagnetic radiation is the usual term right here, and the new term of generating pairs of photons. And you ask yourself now, how will this affect the radiation of a free electron, Cherenkov radiation? Extremely interesting, because now you have three scenarios, okay? First of all, you have photons that are momentum gap photons that are generated by vacuum fluctuations, which is this term. Okay? This term. So this term creates momentum gap photons. And then you have ordinary Cherenkov photons. And then at the end, you have also electron, the interaction of the free electron with the PTC. And each one gives you something different.
And you neglected the A square?
Yeah, I neglected A square. I have, when I was a postdoc, I wrote a paper on A square and I never published it. Now I regret it, because it has some inspirational stuff.
It's so much I outgrew it.
That's the problem. I'm sure that Vlad also has. You see, we are old enough. We have many papers in the drawer that then someday we will regret that we didn't publish. Anyway, so this shows you the scenarios, which is extremely interesting. Okay, so in all three scenarios, the most interesting scenario is when the photon pairs that are generated by the medium interfere with the photons that are generated by Cherenkov radiation in the same direction. So what you would think, for where is it? In the dispersion curve, it's right here, the crossing points. Okay? So you would think that in the crossing points, which is exactly where the photon pairs generated by the medium interfere with the photons generated by the free electron, they will enhance each other and the system will blow up. But actually what happens is exactly, okay, right here. Exactly the opposite. You have an anti-level crossing right here. Right? And this point, this is like the dispersion curve in terms of direction, and they kill each other. They are destructive interference of quantum effects, of Feynman diagrams. So that's part of the interesting part right here. Okay, so interference of the photon pairs that are generated by the electron with the photon pairs that are emitted by the medium without the electron. And this is how it looks. In terms of the dispersion curve, you can see that they have a voided crossing. Now a few words about experiments. So how do you do these kind of experiments? The first thing is that you need to realize that you need to change epsilon fast and large. So the solution, there are several solutions to this. The first one was proposed by Ablonovich in plasma. Plasma is not very interesting to me. Why is that? Because it is a soup. There are so many effects. So chances that in experiments we'll be able to pin down exactly what we want, the effects of the time crystals are very, very small. So that is not a good solution. The other solution is actually epsilon near zero materials. And the idea is that in the wave equation, without any approximation, when epsilon is smaller than 1, all the effects, all the variations are highly enhanced. And what we want is that to choose a probe beam, probe wave, that has long enough wavelength. Here we chose 1,300 nanometers. In other words, it's in the near IR. And on top of that, change the refractive index on the order of 1 in E and Z materials like this, where the rise time is on the order of a few femtoseconds. That's really what we are after. This is why it's an heroic experiment, very, very tough. Okay? So let me move to Eran's presentation, now this one, and I will show you.
So with this Cherenkov radiation, in principle, because you're creating the harmonics, you can create very high harmonics, right? You can create
Yes.
really deep
Uh-huh.
radiation.
Just a moment, let me try to find this. I know it's not this one. Let me see if it's this one. No, there should be one more. I opened too many of them. I should combine. This is it. So this is these are the results of Iran, and I want to tune exactly to the system. Okay. So that's the story. So it turns out, we calculated when we started this, we said, okay, let us calculate the magnitude of the time reflection. So let's say that comes an electric field at 1300 nanometers, as I told you before, at amplitude 1. And we want to know, or intensity 1. And we want to know how large will be the time reflection as a function of the duration of the time window, the rise time, and also as a function of the change in epsilon. So it turns out that if we are able to have rise time of just 3 femtoseconds, okay, and the change in epsilon is 0.8, which is tough. I don't think anyone did it in optical frequencies. Then you get the intensity is about 4 orders of magnitude weaker. If you go to time duration that are longer and longer, we are here more or less in this regime. And we want to do delta epsilon on the order of half, then we are looking at something that is on the order of 8 orders of magnitude weaker intensity. Very, very hard to measure. This is where we are. I need to get rid of this. Okay, so given this, go. Okay, so that's where we are. We are sitting here. That's what we want. We would like to be here. We are now on the order of more or less here. So how do we do it? So of course we start with the Ti sapphire laser, and we shoot it into a hollow core fiber. Or the hollow core fiber, it has inside it some gas, and you get spectral broadening. And after that, we compensate for the phase, and we compress it to around 800 nanometers, but now the spectrum is very broad, to about 5 femtoseconds. And we focus it onto the material. So we started this, what I envisioned is that we will have this in this ENZ material right here, and we illuminate it uniformly from the top, because I wanted it to be uniform, the entire space. And then we take the guided wave right here, and we amplify the guided wave, and we can see time reflection backwards. It turns out this is not a good idea. Why? Because unfortunately, those ENZ materials absorb not a little, but a lot. So if you launch them here, they will not reach far. They disappear. So the other options are to come with the probe either from here or from here. And that's what we do. So let's say you are looking at this one. Okay, so now we took from the same Ti sapphire, we use parametric down conversion from an optical parametric amplifier. We play with delays, whatever, and we look at the pulse at it's about 1500 nanometers, and we launch it here. And we change the refractive index here on the order of 5 femtoseconds. Okay? And what we are looking at is transmission and reflection. So the first thing is before time reflection. We wanted to see what is the impact in the transmission and reflection. If we have time reflection, then the time reflection should have been backwards here. But if you have, because the frequency is different, then it will not come back here, it will come at some small angle here. It is exaggerated because there will be a change in frequency, it will come at some angle here, okay? So that's what you expect. So you want to see that you have a time reflection that goes into this direction. you have Fresnel reflection here, and you have transmission. And you want to see that, synchronize them and measure them. So the first thing is, you can see what happens here, okay? So what we are looking at is the intensity of the transmission, and you can see that the transmission, when you modulate it, transmission went up, and also reflection went up, okay? So the transmission went up and reflection went up. I think the circles are those. So, I'm sorry, transmission went up and reflection went down, okay? And another thing that happens is that when you look at the spectrum, the time refracted, which is the transmitted part, is going to be shifted in the spectrum. So you can see here 15 nanometers shift in the spectrum because of the time refraction. That is very, very interesting already. Now, we can look at the time that it takes, and we see that it takes for the probe, from the probe enters the slab and goes to the other side is about 100 femtosecond by the time it goes from the other side. So that's the delay that you are expecting. So we know how to calculate all of that, and we have one great surprise that we don't know how to answer. And we see that the leading edge, if you look at the center of the pulse, of the infrared pulse, then it turns out that the beginning of that pulse apparently prepares the refractive index, something in the medium, such that when the intensity of the pulse is still very, very small, you already see effects. So either it is because there is a little bit needed for saturation, to saturate the change in the refractive index, and we don't need all this huge intensity, but we see something that if I didn't know that causality exists, I would be extremely surprised. So we tried, this was with 20 femtosecond pulse, and now it's 10. And we have also smaller than that. And the interesting information is, again, the shift. And we see something that the leading edge already of the modulation already creates something, already increases the transmission, already changes the reflectivity. So these are fresh results, and we didn't start writing a paper here because we have more questions than answers. Because of that, I brought my student, Oad, who will come today, and we'll sit with you guys and discuss and see where we take this. Extremely interesting, and we have no answers. Now, it could be that this is the effect of saturation. In other words, it could be that the pulse that we give in, the 3 femtosecond or 5 femtosecond, is very strong, and then the leading edge of it, when just it starts to rise, these are large intensities, already creates enough population of hot electrons, and that already creates, already effects of ENZ for the majority of the pulse. That maybe could explain it.
Are you below damage threshold?
Yeah, we burned quite a few, but along the way, we learned more or less where is the threshold. Okay, there is a lot more to discuss. For example, we looked at what happens on total internal reflection, and we looked at all kinds of things. Of course, if you come near total internal reflection, near the critical angle, all the signals are highly amplified. So chances are that at some point we'll move to work near total internal reflection. And we have all kinds of further ideas, and we'd like to actually delegate some of them to you. If you're interested also in the theory, and we will come and we can give you tomorrow or the day after actually instructions and teach you how to calculate. It's important that you know how to handle this. And maybe I will stop here and answer questions.
Is it possible to observe some interesting effect with low change in refractive index? For example, not for...
If it changes too low, then too weakly, then you don't see the interesting effects. You see? So it needs to change. What will happen is like this. If you change it very little, you are back to the OPA. And it's known for many, many years. We want to see all the effects of the bandgap, the amplification, the non-resonant amplification, create a laser, hopefully. And there are a lot of things of that sort that we would like to do.
It's like with conventional photonic crystals, what they call contours should be high enough to observe a number of effects, like between two materials. Here, in time domain, we have to.
But the relation is not exactly proportional to the change like in photonic crystal. It's kind of complicated.
It's complicated, yes, it's not proportional.
So what do you expect, how much, so it really needs to be like unity, close to unity change in the refractive index to satisfy the parametric change?
We would like to have a unity change that occurs in something that is sub-cycle, in let's say half cycle or 1/3 of a cycle. Now this is realistic actually. You can get on the order of unity change, let's say 0.8 or something, within 3 femtosecond. Actually, what is nice is that the rise time, okay, so this goes to the questions that we don't know how to answer. For example, you'd think that you are looking at, let's say in these materials, that we are looking at electrons that are excited from the bottom of the conduction band to higher up, okay? They are excited by absorption. What's the response time of absorption? Zero. No, absorption is zero. You just go from one level to another, it's zero. It's induced transition. It's zero, no? Why do we see some response there? In the rise time, we see something in the rise time. Why do we see features in the rise time? Now, it could very well be that what happens is that not only it gets to the rise time, and then it tries to get into some kind of equilibrium. Then comes the next question. Okay, so if you think about this material as a Drude conductor, okay? Drude, the model, assumes that you are in thermal equilibrium. How much time it takes to be a Drude conductor? Well, one would think naively that to be a Drude conductor, you need to have several mean-free paths. Let's calculate the mean-free path. Because you know the lattice constant, you know distance between the atoms, let's calculate. And you more or less can tell from the excitation in the dispersion band, from the figures that I got from Vlad and Sasha, you can tell more or less where you are. So you know the energy, you can say more or less, you can more or less get a scale of the velocity. Okay? The material is not in the Drude regime. This is what happens much faster than that, so it's not in thermal equilibrium. So what is the physics of exciting hot electrons and looking at how fast they get to be a Drude conductor? Nobody knows. There's no literature. So we went to talk to some people that do that theoretically. This apparently, from what I know, this kind of questions, were hypothesized but never really studied. So there is a lot. I have some place here. I have somewhere some nice plots to maybe this one.
It really depends on scattering mechanisms, right?
Yeah, but well, we can tell the scattering mechanisms. So I like to end with this slide. This slide says like this. Look, there is a new physics, not so much on the electromagnetic part. Electromagnetism, just this. There's new physics there too. But to some extent, some of that reflects to something that people did 15 years ago. Something already goes back to the 50s. The important part is new physics on light-matter interaction. And all these kind of things that we already looked at it, this is just the beginning, and there is a lot of interesting, the most important one is this. And in my opinion, these are the two. A new source, new light-matter interaction, new laser source, hopefully. Keep in mind that you have a laser, if you can do that, you can have a laser that is widely tunable. Let's say a laser for terahertz. Terahertz is in a regime that there are no good lasers. People do quantum cascade lasers, but if you can do, now terahertz is 10 to the 12, so if you can make changes that are 10 times faster at large enough, you can make a laser source that is widely tunable, no atomic resonance. Maybe it is much better than all the terahertz sources that are there today. Another one, we are actually looking in this. My former student, Ido Kaminer, who is now my colleague, associate professor, has a UTEM. UTEM is ultra-fast transmission electron microscope. So what he does, it looks like a big tower, like a transmission electron microscope, where he excites the electron one by one, and then with a short pulse from the Thai sapphire, and then it runs next to a material. Now imagine that this material is a PTC, and you run next to it. Let's say this PTC has some nonlinear dipole, nonlinear properties. Let's say some piece of lithium niobate, or whatever it is, it will do this. Even not at the PTC, even just when it changes, the refractive index is small. Extremely interesting. This is not resolved theoretically even. So there is now room for putting in the equation some nonlinear dipole moment, classical or quantum, to see what the PTC will do. And there is a lot of interesting stuff.
Radiate in that case. If the change is faster than the flight time near the particle, you will radiate.
Absolutely, that's what we guess. That's why we are interested. So we can do not only theory, this is a regime actually that we can do experiments. Why? Because in the U term, we can use the electron as our detector. If you have a good, eventually single photon detectors at the end, then you can use it and you can see how much photon energy, for every single electron, how much photon energy it sheds and creates a comb. So I think we are now looking into the beginning of a new direction, extremely interesting. And I would like, that's why I came now. I want to get the group of Vlad and Sasha and work with us. But, you know, the theories that are sitting around, like Yevgeny that needs to go to the doctor, or Zubin Jacob, or Kildyshev, or whatever, you're most welcome to interact with us. There's a lot of room for exploration, and I would hate it if it goes then to some other groups, whatever. We will need to capture all the bases.
Jill,
Let's take one more time.
So when you will have actually office here, what would the office mean?
Oh, there is something from Evgeny. You mentioned the capability theory here.
No, Yevgeny, regarding this, I don't think that you are right. I think that there's no need for thermal equilibrium, but you need to have enough collisions. Huh? So you don't need to have equilibrium, but if you don't have even a single collision, as is the case here in our experiments, because we know the mean-free path and we know the velocity. We know the energy. So from there, because it's a created co-absorption, so we can, from that we can more or less guess the velocity, then you will not be in the Drude.